going to move into something which is a great progression of where we just were. We were just looking at our raw materials running out. In our next talk, we're going to go to the next step and say, how do we create new raw materials? How do we create materials which are not in place in nature, and how do we develop on that? And we've got an expert coming on stage to help us with that. Konstantin Novoselov works with this area every day. He's won a very prestigious award, a Nobel Prize for it, and he would like me not to mention that, but I think it's rather quite cool. So, with no further ado, Konstantin, please take the stage. It's all yours.
Thank you so much. It's a great pleasure being here. I would like to thank the organizers for this opportunity to talk, and in particular Anna. It's strange how life twists around sometimes. And so it's going to be a proper scientific talk, so embrace yourself for 15 minutes of formula. Let me start with a little bit of background. So about 10 years ago, we came with this new material called graphene. It's the first two-dimensional material. It's only one atom thick, and yet it has a number of unique properties. It's the most conductive, the most thermally conductive, the most impermeable, the strongest, the most stretchable, and so on and so on and so on. And probably the unique part about this is that all those superlatives are really combined in one material. Now, because of that, of course, it's been tipped to be used in a number of applications, from optoelectronics to composite materials to energy to electronics. And currently we start seeing it coming to life. We start seeing it in composites. Energy is coming, thermal management is working already. For some time, there was a little bit of a scare, can we produce enough of this, because the way how we started with graphene is just peeling graphite from the pencils simply with the scotch tape and just exfoliating it thinner and thinner. And yet now what we have, depending on the particular application you want, depending on the price you want to pay and the quality you want to achieve, we have a number of ways how to produce it, from, I won't go into details, from liquid phase exfoliation to CVD to various epitaxial techniques and self-assembly as well. Now coming to the major part of my work, so it's been quite a nice journey to work and to research into these materials. We are reasonably well funded now. We just finished with the new National Graphene Institute in Manchester. And all my students, they all were very active, bright eyes, bushy tails, always ask me, Costa, now we got all this equipment. Can we finally afford to buy not only the lead pencil, but maybe some other pencils as well? And the answer is, in principle, yes, we can afford this. And the tricky part is that if we start researching and we start exfoliating those, we can produce not only graphene, which is one atom thick material, but also a whole library, a whole class of the new materials, which are two-dimensional crystals. They're all one atom thick, and yet they have a variety of different properties, from the most conductive to most insulating, from optically active to optically transparent, from strongest to the softest, and so on and so on and so on. And that really gives us a very unique opportunity. And let me give you a little bit of the background. If you think about it, our world is really determined by only a few materials. Like electronics, it's all silicon. Construction engineering, like this building, is all relying on steel. Aerospace engineering, the vast majority is aluminum, a little bit of titanium. So we don't notice this anymore. We learned how to live with with the restrictions which are put by those materials, but those restrictions are there. We are basically slaves of those few materials. We are using the materials which we do not want to use. We would like to use some other materials, but the technology, the amount of money spent on those technologies is such that just getting away from those would be is extremely costly, and it's practically impossible. In principle, there are examples how other materials, and ideally what you want is to combine those materials to get some properties which are specific for your applications. And now we're talking about the composite materials and the heterostructures. And in principle, those examples are there already. We do have them in electronics, of course, in the construction, plastics, composites, in airspace, they start to be there now. But those examples are still few and far between. Ideally, what you want, so currently what happens is that if an engineer wants to create a new device, first thing he needs to do is to look through the books what silicon can do for me. What's the band gap, what's the band gap of silicon oxide, and then design a device which is restricted by those properties. Ideally, what you want is to design a device which operates the way you actually want, and then find in the catalog a material which does exactly that. Ideally, you want really to create a material on demand, probably by atom, or at least layer by layer engineering. And then you can basically say that I want my top layer to act as a sensor, my few next layers to act as a solar cell to get power, logic, interconnects, and so on. And with the appearance of those two-dimensional crystals, in principle, we do have this opportunity. Because what happens, I come to my lab and I have a library of those one-atom thick fabrics laying in my glove box, and then I can start, and they all have very different properties, and what I can do, I can start combining them in whichever way I want, and remember, they're still one atom thick. So I can basically pile them into a three-dimensional structure and combine different properties from different materials in one atomic stack. So this stack is not just random. It's actually, it does exist, say, and it's functional as well. So the first 6 layers of this stack would give me a very good transistor. The next few layers would give me a very good solar cell. And you see, I can combine them together as well in one stack, and still it's only 10 atoms thick. So it's extremely thin. You can't imagine how thin it is. So it is flexible. It is semi-transparent if you want. So those examples already exist. Here is an example of a more complex device, which is light emitting diode. You apply voltage and you have light coming out of it. And it's although it is extremely complex, it's still only few atomic layers thick, so it is very flexible. Now, because this technology is a little bit far away, probably, because we do it in the lab, we do it every day, but it will still take years before we start getting into the mass production of those crystals. It took us good maybe 7 years to develop technology to produce graphene. On only one crystal, we need to produce other materials, and we need to produce combinations. So it's a tough job, but lots of groups, lots of scientists around the world do work on this. However, already now we have an affordable technology which does similar task, maybe not as good, but quite similar. Because graphene comes not in many forms, and in particular it also comes as inks as well, just liquid ink. And some time ago we came with inks of other materials as well, insulators or semiconductors, maybe superconductors as well. So we have basically a selection of inks with different functional properties. And what we can do, we can start printing them into heterostructures. So we print one layer of one material, another layer of another material, and then we get some functional device, but now printed. So it's a heterostructure. We combine the properties of very different materials together, and now it is a heterostructure. It's still very, very thin, and yet it gives us some functional properties. Probably not as good as the ideal layer by layer stacking, but it is extremely cheap. It's just a paint. You paint 3 layers of different materials, and you get your solar cell on the wall. Now, just to show you a few examples how we do use this technology already. Here is an example of one of the spin-offs from our university. We started to produce graphene ink, and we started to work on RFID tags. So I won't go into details why printed RFID tags are better than the traditionally produced. There are some basic reasons also related to the raw materials, related to being more ecological. But now we're using, it's a commercial product, it works in both frequencies, and I'm quite happy as a scientist to see that other materials started to be being used in the production of those tags. But what we're trying to do is to go a little bit further, and a part of those RFID tags, it's going to be the major component of the Internet of Things technology. It's used in the communication between different devices. But to make it really smart, you need to produce not only the tag itself, but you need to produce a sensor, so it would read the environment and then transmit it to the source. So those antennas, they don't need batteries, but they can read the environment and provide you with the information. A good example, for example, if you have a pH sensor, you print this antenna on your carton of milk, you print this pH sensor on your carton of milk, you put it into the fridge, then this carton of milk communicates to your fridge. If the milk turns sour, it tells the fridge, and then the fridge orders you a new carton of milk. So, and it's not science fiction. It does work. We do have those sensors already. And ideally, what we want, and because we have a large variety of those crystals, a large variety of the structures which we can print, the large variety of the sensors which we can print not only all the individual sensors, but we can print all the combined sensors in one and have some multitask RFID tags for the Internet of Things application. And I will probably stop here and then just ready for questions. Thank you so much.
Thank you, and this is so exciting. I actually was just visiting a plant where they were printing solar cells on a big roll. So you can transport it on a roll and then just roll it out and put it on whatever wall that you need. When you're doing all of this, what do you find most relevant to meet all the challenges that we're discussing here?
Well, it's I mean, my issue is that because I'm doing it only as a side job. So it's for me it's a good fun. My major task, what I'm paid by the university, is to do science, right? And then and most scientists are doing this. But then incidentally, you just look around and say, wow, you actually can use it for the real technology. And then it's a big challenge because I don't have time to do that. It's you're lucky if you have a good student who would want to take it forward. But in the ideal world, you would need to meet a good entrepreneur who would take it from you and bring it into real life. And I think that's the largest challenge.
In fact, we have a few entrepreneurs here, right? So let's exchange business cards over coffee. But also, I think we should mail your boss and let you focus on this. Do we have time for one or two questions? Raise your hand. Remain silent forever.
Great.
Good. And I know why you don't get questions, because they're all entrepreneurs. And then we got one. There's one hand there. Most of them are waiting for the coffee. They don't want to discuss it in the open. But the bridge is about sharing.
Oh, thank you for a very inspirational talk. It's more of a comment also to the previous speaker. It's a nice anecdote that I remember. It was the former oil minister Sheikh Yamani warning his OPEC colleagues in the 70s or 80s that the Stone Age didn't end because we ran out of stones. And so when we talk about raw materials, then it's, you know, the raw materials that we have, and this graphene is an excellent example. The raw materials questions that we have are not necessarily the raw materials questions that we have tomorrow. That's all.
I agree. So I think it's the having a flexibility in designing materials for what we actually need to use them and where do we need to use them would set us free from the raw material challenge, and it would save us energy, save us resources, and we would just get much more efficient in that respect. Thank you.
Thank you ever so much.